Hello students, in this video we are going to see closure of a set. Closure of a set. Definition: let XD be a metric space. Let XD be a metric space and A is a subset of X. The closure of A denoted by A closure is the union of A and the set of all its limit points. That is, A closure is equals to A union A dash. In other words, A closure is the set of all points of A together with all those points which are arbitrarily close to A. That is X belongs to A closure if and only if SR of X intersection A is not equals to 5 for all r greater than 0. See here what is definition of closure of a set. XD be a metric space and A is a subset of X. The closure of A is denoted by A closure. It is the union of A and set of all its limit points. That is, A closure is equals to A union A dash. In other words, A closure is the set of all points of A together with all those points which are arbitrarily close to A, means limit points of A. That is, X belongs to A closure if and only if SR of X intersection A is not equals to 5 for all r greater than 0. Let us see examples on closure of a set. Example: let RU be the usual metric space, then find the closure of following set in RU. First one is Z. What is the definition of closure of a set? If XD is a metric space and A is a subset of X, then closure of A is equals to A union A dash. A dash is nothing but limit points of A. Therefore, Z closure is equals to Z union limit points of Z, which is equals to Z union. In previous video, we have seen limit point of Z is 5, which is equals to Z. Second example is Q. Q closure is equals to Q union Q dash, which is equals to Q union. Limit points of Q is R, which is equals to R, because Q is a subset of R, therefore Q union R is equals to R. Third example is R closure. R closure is equals to R union R dash. R union, we know that what is limit points of R, which is R. R union R is R. Fourth example is open interval 0, 1. In previous video we have seen that limit point of open interval AB is nothing but closed interval AB. Closure of open interval AB is equals 0, 1 is equals to open interval 0, 1 union limit points of open interval 0, 1, which is equals to open interval 0, 1 union closed interval 0, 1, obviously which is equals to open interval 0, 1. Therefore closure of open interval 0, 1 is equals to closed interval 0, 1. Fifth example is semi-closed open interval 3, 4. Closure of semi-closed open interval 3, 4 is equals to semi-closed open interval 3, 4 union semi-closed open interval 3, 4 limit points or limit points of this interval, which is equals to semi-closed open interval 3, 4. In previous video we have seen semi-closed open interval, limit points of semi-closed open interval is equals to closed interval AB. Therefore this is union closed interval 3, 4, and union of this set is nothing but closed interval 3, 4. Let us take one theorem. Let order pair XT be a metric space, and A is a subset of X. Then first, A closure is a closed set. A closure is a closed set. B, A is closed if and only if and only if A is equals to A closure. Part C is A closure is the smallest closed subset of X containing A, and last is B. A closure is the intersection of all closed subsets of X containing A. Let us see proof of this theorem. First we prove part A. What is we have given? X is a metric space and A is a subset of X. In first part we have to prove that A closure is a closed set. A closure is a closed set. For this we will see A closure contains all its limit points. Proof of part A. Let X be a limit point of A closure. Let X be a limit point of A closure. Therefore, for given epsilon greater than 0, there exists Y belongs to A closure such that distance between X and Y is strictly less than epsilon by 2 by definition of limit point. Here what we have taken, X be a limit point of A, therefore for given epsilon greater than 0 there exists Y belongs to A closure such that distance between X and Y is strictly less than epsilon by 2 means Y is belongs to S epsilon by 2 of X. That means open sphere centered on X contains at least one point of A closure other than X. That is, since here Y is belongs to A closure, that is either Y is belongs to A or Y is limit point of A by definition of A closure. By definition of closure of a set. There exists Z belongs to A such that distance between Y and Z is strictly less than epsilon by 2. See here, if Y is a limit point of A, then by definition of limit point there exists Z belongs to A such that distance between Y and Z is strictly less than epsilon by 2 means open sphere centered on Y contains at least one point of A other than Y. Now d of x comma z is less than or equal to d of x comma y plus d of y comma z by triangle inequality. Which is strictly less than epsilon by 2, which is equals to epsilon. Therefore, distance between x and z is strictly less than epsilon. That implies x is the limit point of A and hence X is belongs to A closure. See here, what we get? Distance between X and Z is strictly less than epsilon means open sphere centered at X with radius epsilon contains one point means Z of A other than X. Therefore, X is the limit point of A and hence X is belongs to A closure because A closure is equals to A union A dash. Obviously, X is belongs to A closure. That implies A closure contains all its limit points. A closure contains all its limit points. That implies a closure is closed set. A closure is closed set since by theorem. Since by known theorem. Because we know that if A contains all its limit points, then that set is closed. What we have to prove? A closure is closed set. For this we will show that a closure contains all its limit points. Let x be a limit point of a closure. Therefore, for given epsilon greater than 0, there exists y belongs to a closure such that d of xy is strictly less than epsilon by 2. Since y belongs to a closure, that is either y belongs to a or y is limit point of a. Therefore, there exists z belongs to a such that distance between y and z is strictly less than epsilon by 2. Now, by using triangle inequality, we get d of xz is less than or equal to d of xy plus d of yz, which is strictly less than epsilon by 2 plus epsilon by 2, which is equals to epsilon. That is, distance between x and z is strictly less than epsilon. That implies x is the limit point of A, and hence x belongs to a closure. That implies a closure contains all its limit points. Therefore, a closure is closed set. Hence, proof of part A is complete. Now we will prove part B. In part B, we have to prove A is closed if and only A is equals to a closure. First we assume that A is closed. We have to show that A is equals to a closure. We know that a closure is equals to A union A dash, but A dash is always subset of A, because what is our assumption? A is closed. Therefore, A closure is equals to A union A, which is equals to A. That is, A closure is equals to A. Hence, the proof. Now, conversely, assume that A closure is equals to A or A is equals to a closure. We have to show that A is closed. We have to show that A is closed. Clearly A is closed set. Clearly A is closed set, because in part A we have proved that A closure is a closed set. A closure is a closed set, and our assumption is A closure is equals to A. Therefore, A is closed set. Hence, proof of part B is complete. Now, we will prove part C. First, we show that A is a subset of A closure. In part C, we have to show that A closure is the smallest closed subset of A containing A. First, we show that A closure contains A. Since A closure is equals to A union A dash, that implies A is a subset of A closure. Also, A closure is closed set since by part A. In part A we have proved this since by part A. Okay. Now to show that A closure is the smallest closed subset of X containing A. Let B be any closed subset of X with A is a subset of B or B contains A, and let X is belongs to A closure. If X is belongs to A, that implies X is belongs to B. Since here we have taken A is a subset of B. In case X does not belong to A, that implies it is limit point of A. Therefore, by definition of limit point, then for given epsilon greater than 0, there exists y belongs to A such that distance between X and Y is strictly less than epsilon, but Y is belongs to B because A is a subset of B. Also, since A is a subset of B, therefore X is limit point of B. Therefore, X is limit point of B. The set B being closed. X is belongs to B, and as such A closure is a subset of B. Therefore, given any closed set B contains A, we have B is a subset of B contains A closure and A closure contains A. Therefore, A closure is the smallest closed subset of X containing A. Here we have to show that A closure is the smallest closed subset of X containing A. First we show that A is a subset of A closure. Since A closure is equals to A union A dash, that implies A is a subset of A closure. Also, A closure is closed set by part A. Now to show that A closure is the smallest closed subset of X containing A, let B be any closed subset of X with A is a subset of B and X is belongs to A closure. If X is belongs to A closure, that means X is belongs to A union A dash. If X is belongs to A, that implies X is belongs to B, since A is a subset of B. In case X does not belong to A, it is the limit point of A. Therefore, by definition of limit point, for given epsilon greater than 0, there exists y belongs to A such that distance between X and Y is strictly less than epsilon, means X is limit point of A, means open sphere centered on X with radius epsilon contains Y point other than X, but Y belongs to B because A is a subset of B. Therefore, X is also limit point of B. The set B being closed because X is belongs to B, and as such A closure is a subset of B, because here we have taken X is belongs to A closure and we get X is belongs to B. Therefore, A closure is a subset of B. Therefore, given any closed set B contains A, we have B contains A closure and A closure contains A. Therefore, A closure is the smallest closed subset of A containing A. Hence, proof of part C complete. Let us see proof of part D. In part D, we have to prove A closure is the intersection of all closed subsets of X containing A. Let capital M is equal to intersection of set of all B is a subset of X such that B is closed and A is a subset of B and A is a subset of B. What is M set? It is intersection of all sets B is a subset of X such that B is closed and A is a subset of B. Here we have to show that A closure is equal to M. We know that arbitrary intersection of closed set is closed. Therefore, M is closed. Clearly, M is the smallest closed subset of X containing A. Clearly, M is the smallest closed subset of X containing A. Therefore, A closure is equal to M. See here, let M is equal to intersection of set of all B is a subset of X such that B is closed and A is a subset of B. We have to show that A closure is equal to M. We know that arbitrary intersection of closed set is closed. Therefore, M is closed, and clearly M is the smallest closed subset of X containing A. This is by part A. Therefore, A closure is equal to M. sorry, here since by part A, sorry, part C. In part C, we have proved that A closure is the smallest closed subset of X containing A. Hence, proof of this theorem is complete. Thank you.